Thank you very much, Ivan. Thank you for being here. I work in the Center for Advanced Technologies in Telecommunications. I work with the team of Professor Panoir on the field of cooperative networking. And I'm going to give a presentation about our work. It's my great pleasure of being here. So in my presentation, I'm going to present some motivations of using cooperation in wireless networks. Then we'll see a cooperative MAC protocol that we call CoopMAC. I'm going to describe an implementation effort we've done for CoopMAC, and then we'll see some conclusions in future work. So as we know, the wireless channel is by nature a broadcast channel. And when we have to transmit broadcast packets, this is very convenient. But once we go to the unicast case, the broadcast nature of the wireless channel gives us some difficulties. So we try to figure out ways and schemes to deal with this broadcast nature. On the other hand, one other characteristic of the wireless environment is that the quality of the channel changes depending on the position of a station or depending on the time or on the distance between the two stations. So these wireless networks have this multi-rate capability. 802.11b has these 4 rates, 1, 2, 5.5, and 11 megabps per second. And the basic rule is that we try to adjust the transmission rate in order to have a reliable communication which is acceptable bit error rate or packet error rate. So the classical MAC protocols try to find ways to deal with the difficulties of the wireless medium. And what they do is that they put all the stations in a common network being competitors. So everyone competes for the medium, and once it gets the medium, it can transmit. Our idea is to change this functionality into a cooperation mode, cooperative mode. Let's see a simple example. Station 1 is far away from the access point, so it experiences a bad channel, and it can transmit to the access point in 1 megabps per second. So when station 1 transmits, it needs the blue period of time in order to have a slow transmission in this rate. After the end of the transmission of station 1, station 2 has the ability to transmit its own packet, and because it's close to the access point, it can transmit in a high rate, let's say in 11 megabps. So the whole procedure of the two transmissions lasts the blue plus the red line. So our idea is, instead of transmitting from station 1 direct to the access point in a low rate hop, why not transmitting in a fast hop to station 2 and then retransmitting the same packet from station 2 to the access point? In this way, the transmission of the packet from station 1 to the access point lasts shorter period than in the previous case. So then station 2 can transmit its own packet, and the whole duration is shorter than the previous case. That means that this is a benefit for both the stations, station 1 and station 2. So based on this simple scheme, we designed a CoopMAC protocol that we call a cooperation protocol that we call CoopMAC. And I'm going to describe it right now. Under this protocol, every station maintains a table that we call cooperation table or Coop table. In this table, the station maintains information about all the neighbors in the area that can be candidate helpers for its transmission. So what is a candidate helper? A candidate helper is a neighbor that experiences good channel with both the transmitter and the receiver of a packet. So in our example, station 2 is helper of station 1 because station 2 has a good channel with station 1 and with access point. So every station maintains this table, and in every row of the table maintains information about the identity of the neighbor, let's say of helper 1. It keeps the MAC address of helper 1, the time the last packet from helper 1 is heard, and the two transmission rates, the rate between him and the helper, and the rate between the helper and the destination. So how the station, let's say station 1 in our case, can learn the rates for these two hops. Actually, we have three hops that the station must know. First, the direct rate from itself to the destination, which is known. And second, the rate from the station to the helper and from the helper to the receiver. In order for the station to learn the rate for the first hop, it can hear the RTS, CTS exchange between the receiver, which in our case is the access point, and the helper. And from there, it can, based on the SNR, it can learn the rate for the hop 1. Now, as regards the hop 2, which is the hop from the helper to the access point, the data packet that is transmitted from the helper to the access point and is heard by the station has in its physical layer header the information about this rate. So reading this information, the station learns the second rate hop. So the station having this table, once it wants to transmit a packet, it goes through the cooperation table and it finds the best helper. Which is the best helper? The best helper is the helper who gives the shortest time for this two-hop transmission from the transmitter to the helper and from the helper to the receiver. And of course, this time must be shorter than the time that the direct transmission would last. Otherwise, there's no meaning to use a helper. So once the station finds a good helper, and once the information that it maintains in its CoopMAC table is not stale, decides to use this helper. So after it decides to use a specific helper, station 1 transmits an RTS packet which now contains the MAC address of the receiver plus the MAC address of the helper. So both the receiver and the helper are informed for the intention of station 1 to use station 2 as a helper in order to transmit something, a packet to the access point. Station 2 sends a new control packet that we call HTS, which is helper ready to send, with which it informs both the transmitter and the receiver that yes, he wants to participate in the cooperative transmission. He will help. If station 1 does not receive this HTS, continues with a direct transmission. Otherwise, if station 1 and the access point receives the HTS, then the access point transmits the CTS to station 1. That is heard by station 2 also. So after the exchange of this control packets handshake, there is the transmission of the data packet, which is done in 2 hops from station 1 to station 2, and then from station 2 to the access point. Some details here. This packet that is transmitted from station 2 to the access point is transmitted directly after shift period, after the reception of the packet from station 2. So there is not competition for the medium by the station 2 in order to transmit the packet in the second hop. It transmits the packet directly after a shift period. The same happens with the control packets. The interframe period between them is shifts. So after the reception of the data packet from station 2, the access point sends this acknowledgement to station 1, informing that the reception of the packet was successful.
I have a question.
Yes.
Is there a timeout period at station 2 if the packet from station 1 gets dropped?
Excuse me?
If the packet from station 1 gets dropped on the first hop, is there a timeout period?
Yes. Yes. So you mean if station 2 does not transmit the packet to the access point?
No, the first hop. Station 1 does not for some reason the packet gets lost between.
Yeah, even if it gets lost in the first or in the second hop, there's a timer that makes station 1 realizes that the packet is not transmitted in the right way.
Okay. So that is just regular MAC.
Yes. The same with the HTS. If station 1 does not receive the HTS after a specific threshold, it realizes that the helper won't participate.
That's what I wanted to ask. How comes that HTS and CTS do not collide? So there's some time gap. CTS is not sent after.
Yeah, CTS will be transmitted after the reception of HTS. So if the timeout is expired, then the...
Like what if there is no HTS?
Sorry?
Like what if there is no HTS to send?
If there is no HTS to send, then the 2 stations will continue the transmission by the direct mode, using the direct
Like
mode.
station 1 will send RTS, right?
CTS is postponed.
And then CTS, there is no CTS, for example. Station 1 is able to send to the access point directly.
Yes, it is able, but this link is very slow. Station 1 can communicate with the access point directly. But this link is very slow.
No,
So
I assume that the link is very, like 11 Mbps, very close to the access.
No, but in RTS you send that you will use the helper.
How do you say that? Okay.
You modify the RTS.
yes.
Announces
RTS,
itself.
yeah, it announces that there will be a helper who will help. So it's not the original RTS. Yeah, it's a new RTS that...
Direct communication.
Yeah, we call it CoopRTS. This slide is like there should be CoopRTS there rather than just RTS.
Yes,
It's
yes,
a
yes.
Slide type of mistake.
This one. So is this infrastructure mode or ad hoc mode?
This is an infrastructure mode.
How do you expect I think infrastructure node, any client has no notion of its neighbor. Its only neighbor is the access point. So
Yes, but station can hear each other. They don't communicate, they don't exchange packets, but they can hear each other.
so when you
So we don't expect for the neighbors to exchange packets.
right, but when you send a data packet through the helper to the AP,
Yes.
you are sending directly to a helper, right? Without the AP. So how will that work if you are in the infrastructure mode?
This is okay. This is not 8.11.
It's modified. You have to modify the infrastructure.
Yeah, this is another protocol. It is based. It has many commons with 8.11, but this is we modify the functionality.
How do you know the rate from station 1 to station 2?
That was in the,
From station 1 to station 2, we receive the RTS, let's say, from station 2 to the access point. And then we are based on the SNR. We assume that the transmission power is known. So we know the reception power and we can decide about the rate.
So you do an SNR to rate mapping.
Yes. So we don't need to receive a direct packet. Whatever packet we receive from this station is enough for us to approximate the rate we're going to use to transmit to this station. Yes.
I think it's mandatory to use RTS, HTS, CTS, right? So what if the packet size is very small?
No, it's not. It's not mandatory. It's not mandatory. If the packets are small, we can transmit the packet direct to station 2, to the helper. So there is a version where we don't have the control packets as in 8.11. If the packet is really small, then you don't have to use the control packets and you can transmit directly to the helper. And maybe he will help, maybe he will not help.
Without HTS, how do you, kind of do this?
But the HTS is there to inform the transmitter that he will help. So if the packet is really small, it does not worth to ask him. You transmit it. If he intends to work to help, he will help. He will retransmit it. Otherwise, you lost your packet.
So after you lost the packet, you are going to
Sorry?
transmit it to
Of course, you'll retransmit it. You won't get an access.
transmit it to the helper or to transmit to accept.
Excuse me?
So if the helper does not help, you will transmit to helper again or you transmit to accept.
It depends. We can use another helper, or you can transmit directly. It depends on the instance of your neighborhood.
Like, do you have an algorithm for that?
Yeah. You go through the helpers.
Yeah. We go through to the CoopMAC table. We go through the CoopMAC table. We compute this time that it is needed for the 2-hop transmissions, and the station who gives us the best time is the station who will help. Between two stations who gives the same time, let's say that we have two stations who has 11 megabit PS in the first hop, 11 megabits in the second hop, we use the one who has the most recent information in the CoopMAC table.
The version is without control packet, you send a packet to the helper, and you don't hear the arguments from the accept point. You don't know if the helper really want to help. Even the helper want to help, he can have. First when you lose the packet in the second hop. So in this case, what the sender are going to do? They're going to transmit directly or wait for help to transmit.
You mean the helper may retransmit the packet in the second hop?
Yeah.
Without what?
So you don't
No,
know.
the question is if the second hop drops the packet, in case without RTS CTS,
Okay.
What would you do? Would you retransmit it the same?
Sure. This is a lost packet. This is a lost packet. It doesn't matter where you lose it. It's a lost packet.
Each hop has its own. No, the problem is the sender does not know if the helper.
No, the receiver sends the ACK. The receiver sends the ACK.
There's only one egg.
So it's only one ACK.
Yeah.
So once,
That's your game.
yeah.
Both of
There's
them
only one ACK, but there are two possible senders. The sender and helper both for the retransmitter. So who are going to retransmit?
Who will gonna?
who will retransmit?
The question is who's going to retransmit?
No. The
Helper will not-
transmitter will retransmit.
The helper
The,
cannot retransmit.
the helper does not participate in the decision. The helper just gets the packet and retransmits it.
Okay.
Just help with the retransmission. He does not care otherwise if the packet is there or not, is in the destination or not. This is controlled by the transmitter.
Again, it has to go through two hubs. I mean, retransmission also, right?
Again?
The retransmission also should go through two hubs now.
Yes.
But not necessarily the same
No.
hub.
It depends. It depends. It depends on your CoopMAC table.
Or you mean when packet is lost?
You may,
Transmit, it can go through different paths.
yeah.
But then
You
that
can
will
even
be
go
solved.
directly if there is no.
You can go directly or you can go by a different path.
So
But when
things
you
have
think of-
changed.
Yeah, because your time expired, right? I mean, your times are changing.
Yeah.
Last updates changed, right? And stuff like that.
So this is one step further than the basic thing you can do. You can transmit directly. But one step further, you can improve your time transmitting in the two hops manner. If this won't work, you can choose another helper or you can transmit directly. Okay? Okay. So this is the protocol, and here are some results from the simulations we had. So this is the throughput as the number of nodes increases, and the red lines are the CoopMAC lines, the blue lines are the legacy 8.11. And each pair of blue and red line is the throughput for different sizes of packets. So what we can see here is that indeed CoopMAC increases the network throughput, and as the length of the packet increases, this gain is higher. Something interesting is that as the number of nodes increases, the legacy 8.11 decrease has a slight decrease in the throughput. This is because of the collisions. As the stations become more and more, there are more collisions in the network, so there is a degradation on the throughput. On the contrary, CoopMAC protocol, in the CoopMAC protocol, as the number of nodes increases, the throughput increases, and this is because the stations who experience a bad channel with an access point, as the number of nodes increases, have a higher possibility to find a good helper to help them transmit in a fast way their data.
So how many flows were there?
Sorry?
How many active flows are here in this? What's the offer?
What do you mean flow?
I think per node.
Per node, what's offered
Per
load?
node.
So what is
Is
the
it
offer?
saturation?
It's saturation, yes, it's saturation.
So when the number of nodes increases, each has its own traffic towards the AP.
Yes.
Okay, so in this simulation, did you have nodes which have which see different channels? Obviously, you had nodes which see different channels to the access point, namely some see 1 megabyte, some see 11 megabytes.
Yeah. There's a uniform distribution of the nodes in the cell.
Okay, so there was no rate adaptation or anything?
No.
So there were a bunch of guys who had good channels and a bunch of guys who had bad channels?
Exactly.
What was the percentage of guys who had good channels?
Based on distance?
It's uniform, so it
There
should
is a
be-
uniform distribution.
It should be the same, right?
Yeah.
Is it single access?
Yes, there is one access point and many stations, and there is an infrastructure network.
And NS?
Sorry?
Is this NS?
No, it's
This is simulation, right?
yeah, there's simulation in C code.
Let me see the
Oh,
number.
okay.
It's 3, right? 3 megabits.
3.5.
Yeah, no way.
What's 3.5?
3.5 megabit per second for less than. No, in general, the total throughput is
Okay, so here we have a curve how the throughput gain goes as the payload length gets bigger. So what we can see is that after a specific value of the payload length, the gain is high. But for small payloads, we have 8.11 does better than CoopMAC, and this is normal because we have this increase on the overhead from the control packets, from the added shifts. So as we said, for small packets, it does not worth to use the control packets for the communication.
Did you simulate without control packets for small size?
We simulated, yes, but I don't have any results. Yes, we simulated also with.
Any gain.
Sorry?
You don't have any gain even though you don't use control packets for small packet size.
What do you mean change? Yeah, you have. This what I am showing now is using the control packets.
Right, so most the overhead is from the control packets.
Yeah. Once you get rid of the control packets in the small payloads, you do very well with the CoopMAC again.
There is another cutoff point where it will become bad again, right? Because there is still the 2 5-layer overheads. When you transmit twice, there is 2 5-layer overheads. So the cutoff point will move down to
Yeah.
like maybe less than 80 bytes somewhere there. There's a cutoff point below which cooperation is not good going straight. So if you have 10-byte packets, transmit directly, right? So basically,
Well, it's only because your header is
physical
twice.
error, physical error is 192 microseconds added every time. So just takes time.
So one more figure with the simulations. Here we see the probability distribution of the channel access delay, which is the time from the moment the packet is on the head of the line until the moment the packet is served, is transmitted. So even for the channel access delay, CoopMAC does better. So from the simulations, we can see that there are benefits even in the throughput and in the delay of the network. So what we did is that we went one step further, and we have started trying to implement. This is mine. Give me 1 second to turn it off.
Why is everybody looking at me?
Your phone is the only one that works.
That's true. By design.
So we started trying to implement our protocol, and what we did is that we decided to use the host IP driver. I think that most of you should be familiar with these kind of things as you work here. So we use the host IP driver. It's an 8.11b driver in a Linux platform. And as, of course, again, I think you know, we had these limitations from the firmware. So using, trying to implement our protocol, we faced up a lot of problems because the time-sensitive functions are controlled by the firmware. So trying, let's say, to add the HTS packet, I'm mentioning one example, we had a hard time. I'll explain our challenges. What we should see in this figure is that we added a new header, what we call CoopMAC header or cooperation header. We added just after the 8.11 MAC header in the beginning of the payload. And we maintain there the source address, the destination address, and the helper address. And these are the original source address and the original destination address. So they may be the same with the addresses that 8.11 MAC header has, but they may be different, because the source address and the destination address in the 8.11 MAC header may change in the 2-hop trip. So what we do is that we use this header in order to guide the stations in the route of what's going on. What is this packet, where it is going, who is the helper. Let's see the functionality modifications we've done. As regards the transmitter, now the transmitter based on the CoopMAC table selects the best helper. This is the one new functionality. So every time it wants to transmit a packet, it goes through its CoopMAC table, it does this computations, and it decides who is the best helper. Then it inserts the CoopMAC header into the packet with the appropriate information, and it transmits the packet. On the helper side, the helper receives the packet and checks the CoopMAC header and checks whether it is a helper or not. If it is a helper, then it resets the helper address in the CoopMAC table, because now this is the second hop, so the new receiver must realize that there is no helper for this packet, and retransmits the packet to the receiver. As regards the receiver, it gets the packet. If it is the receiver, it extracts the payload plus the CoopMAC header. It gets rid of the CoopMAC header and it gives a packet to the higher layers. And what it does is that every time it gets a packet that is that is useful for the update of the table, it updates the CoopMAC table. So how we implemented the CoopMAC table maintenance? As I mentioned, under the CoopMAC protocol, a station updates the CoopMAC table passively. So every time it receives a packet from a neighbor, it updates the specific record in the CoopMAC table. Instead of following this passive approach in the implementation, we decided to use an active approach under which every station transmits a hello packet in a periodic manner. So in this packet, we broadcast information about the rates in the 2 hops. We did that so we could have a better control of the test bed we make, because it's hard to be based on the transmissions of your neighbors in an environment that you have 10 laptops, let's say, that they don't work appropriate, like in a regular mode. So in this way, we control the decisions about the helpers. Every time a station receives a hello packet, it updates the corresponding record in the CoopMAC table, or it adds a new entry. The entries in the CoopMAC table are very similar to the entries of the CoopMAC table we designed, except of the fact that now here we keep the time that we received the most recent hello packet from this station instead of any packet.
So this hello packet is sent how often?
This is we can control that. It's a value that we control. So we do several experiments with different values in the hello packet.
Question.
Period.
Was anything moving when you tried these experiments? It was stationary.
Yes, we make a kind of we emulate a kind of mobility by disabling or enabling helpers. So if you disable a helper, then he tries to find a new helper because this helper is not anymore active transmitting these hello packets.
These are application level.
No, we implement it in the Mac layer,
Driver.
in the driver. So in the driver, even the hello packet, we have it in the driver. So we wanted to keep the whole functionality in the low level. So it's a broadcast packet of the driver that in the payload has information about the rates. Let's see now the design challenges we faced during the implementation of our protocol. Our first problem was that we wanted to replace the initial control packets, the RTS and the CTS, with the three-way handshake RTS, HTS, CTS. So, and we wanted this to have an internal time of shifts period. Unfortunately, we couldn't do that because we can't change the functionality of the firmware. So what we did for the moment is that we suspended the control packets and we transmit the data packets directly in the two hops. So now there is no control packet in the implementation of the protocol. The second challenge we had was that we wanted to transmit the data packet without competing for the medium in the second hop. So eventually this would be for the neighbors would be a continuous transmissions. We want not to the neighboring stations to be able to understand that this is a two-hop transmission. And of course we don't want the delay that we have competing again for the medium in the next hop. Unfortunately, again, because we can't control the firmware, we are not able to transmit after shifts. So what we do in this approach is that we compete again for the medium in the second hop and we transmit the packet, so we add the overhead in our protocol. Finally, what we wanted to do is that we wanted to have one NAC packet, as we said. So we want to have a NAC packet from the receiver to the transmitter after the two hops transmission of the data packet. Again, we couldn't handle this directly, so we tried to emulate this thing indirectly using these two approaches. In the first approach, we used the broadcast packets. So in 82.11, when you use broadcast packets, there is no acknowledgement. But the problem is that acknowledgement at all. So you just transmit without realizing if your packets are there. And then what we saw is that in the higher layer, we had short TCP windows because we couldn't guarantee reliable communication in the MAC layer. So the other approach was the Unicast approach. We transmit the data packet, we get an acknowledgement, we again transmit the data packet, we get the acknowledgement, one more acknowledgement, but at least we have reliable communication between the stations. Of course, again, this is not 100% reliable because you may lose this packet and you are not able to understand that. But at least it's better than having nothing. Yes?
Is this Unicast approach still faster than a direct hop?
Yes, yes. After that, I have some results from the implementation.
So there's no broadcast of the ACK. It's all Unicast, essentially.
It's all Unicast, yes. This is a normal 82.11 ACK. We can't touch the ACK. We can suspend it, we can't modify it, we can't do anything with the ACK. So we have this basic implementation scheme, and we are very happy that at least it gives us good results. So what we did is that we set up a very simple test bed, one transmitter, one receiver, and several helpers. The helpers are, I have this figure to show you how we pick the helpers, because I use this notation all the time on the next figures. So helper A1111 means that this is, when a helper is in this region, means that this helper gives 11 megabps to both hops. Helper 5.511 means that one hop is 5.5, the other hop is 11. So depending on the area that the helper is, gives you different rates in the two hops. Of course, what we did is that we forced the rates. We didn't walk around with the laptops to find the ideal spot. But so we transferred some files, big files, from the transmitter to the receiver using different helpers, and we measured the transfer time. And what we see is that the CoopMAC does really better than the 8.11. So what we can see in this figure is this is the legacy 8.11 for 1 megabps direct link, and these are different helpers, two-hop transmission with different helpers. So as you can see, even with a helper that is 5.5, we have a better throughput than the direct transmission.
You always had only 2 hops, right? Not more than 2.
No, only 2 hops.
Helper couldn't have another helper.
Excuse me?
A helper couldn't have another helper.
No. So this is a similar figure. Now we have a direct link of 2 megabps. So again, we can do good with the helpers that have 5.5 and higher. We can't use this helper that we used in the previous experiment. But again, with if you have a direct link that is 2 megabps, you can still have a lot of benefits using the two-hop transmissions. Finally, what we did is that we disabled the cooperation, we disabled the two-hop transmission, and we used the driver we built to transmit directly. So we wanted to try to find out if we have any overhead in the transmission from this CoopMAC maintenance, from the insert of the CoopMAC in the payload, from the strip of the CoopMAC in the receiver. So what we see is that we have exactly the same results with host IP, which means that the overhead, that the computational overhead is zero. Now, finishing my presentation, I'm gonna give some conclusions. So what I presented, what I described is a high-performance cooperative Mac, which is compatible to the 8.11. The first try to implement the protocol is very promising. It shows that CoopMAC works well in the real environment. And we hope that we'll continue with this work. Actually, we have a demo. It's a very nice demo. It's a full functional demo that shows the benefits of CoopMAC. We have a transmitter, a receiver, 2 helpers. We stream a video from the transmitter and we receive the video with a receiver. And then we play with the helpers. So one helper is a helper 11 megabps and 11 megabps, and the other one is 5.511. So what we do is that dynamically we change the capability of the helpers. We suspend the hello packets so the helpers stop being helpers. And what we can see is that the transmitter dynamically selects a new helper If you can find a helper, it transmits directly in a slow rate, and you can see all these changes affecting the video quality on the receiver. So as you unplug, let's say, the card of the good helper, for seconds the video on the receiver freezes, and after a while it starts again receiving the video from the direct mode, let's say, which has a much worse quality. You are welcome to check our the project's site, which is this. So as regards the future work in the implementation field, we are setting up now a large testbed, and I already say large, and I laugh now because I've just saw your testbed, and when I was writing the presentation, for me this is large because we play with 3, 4, 5 laptops, and now we are setting up a testbed with 15 laptops. But for you, this is.
If you look at the papers, everything above 10 is large.
Yeah,
So
yeah. Yeah, but it will be very interesting. I mean, you have a powerful tool here, and I hope that we'll start using this testbed here. So what we are currently trying to do is that to set up a testbed of 15 machines and play with this testbed and do some experiments for voice over IP, see how the helper is affected by helping, see how mobility or the change of the helpers affect the whole thing. So as I said, we are trying to see how we could use Orbit for our implementation, and I think we'll do it. And on the other side, in parallel, we study the potentials of introducing cooperation at the higher layer. So to have a 2-layer routing, we can say a fast routing in the MAC layer, which can give you one-hop route based on the conditions of the medium, and then in the higher layer, in the root layer, something another root protocol that is collaborate in a way with the MAC layer protocol, and find in this way the ideal route. On the other side, we try to combine the CoopMAC protocol as I described it with cooperative diversity at the physical layer. So we try to find how the helper and the transmitter can cooperate in the physical layer also, not only in the MAC layer, in order for the receiver to combine the two signals and to get the received packet right. Another thing we do, and someone mentioned, is that we try to see how we'll extend this idea in the ad hoc environment, and how it will behave in an ad hoc environment, and which would be the modifications in the ad hoc environment, because there will be several problems. We don't have hidden terminal problem in the infrastructure network. Then we introduce more complicated environments. So this was my presentation. It would be my pleasure to answer to your questions. Yes.